Hello, dear students. This is your professor, Jaron Haber. I am sorry we're not having class today in person, at least with me there, but I'm hoping that this introductory video that continues what you were doing last class with me will be interesting and engaging. And yeah, this is for QSS20, Modern Statistical Computing. And let me share my screen. So today we're continuing on with the supervised machine learning from last time and deepening a lot into a different method. This time we're talking about decision trees and optimization. And last time we focused on logistic regression. So I'll give us a quick recap first. But first, our learning goals. So today we're trying to get comfortable with the vocabulary and rationale for model optimization, learning some basic mechanics of a few different models. Logistic regression we talked about last time. Go through cross-validation. That's a really important tool to understand, and get experience implementing, comparing, and optimizing supervised machine learning models. And then some basic visualization, including some cool 3D stuff I think you'll probably enjoy. So last time we went through the basics and a walkthrough of some of the simple steps. We'll recap some of that today, and then go into overfitting as a problem, and then decision trees optimization, and a notebook that I will walk you through. It's a little more dialogical than you might be used to. Okay, so first the recap. So I invite you just to consider for remember, we talked about the basics of supervised machine learning last time. So what do you remember? Just like come up with one thing. Okay, I hope that jogged your memory just a little. And if you have a classmate with you, I invite you to pause and just talk it over with them. But for the purposes of the video, let's keep going. So some basics to remind you of here. Features are the things the model is built on. So in the case of the examples we're using for last class and today, these are words in reviews. And we're predicting a label. So that could be whether it's spam or not spam, whether it's a happy review or not a happy review. Benefits of this is you can scale the approach. It tells you what features matter the most. And you have to think about what you're trying to measure here. So if you really care about avoiding false negatives, like not accidentally telling someone that they don't have cancer when they do, for instance, like you'd rather err on the side of making false positives, like tell them they do even if they don't, just so they have the information. Like, yeah, that could also be pretty bad, but it's much worse to miss it when it's actually there. Or if you're trying to avoid false positives, so like if you have a spam detector that just keeps on telling people that they have spam or when they don't, that could be also really annoying. So for the first case, you care about recall. You want your models to not miss things that are actually there. A lot of when you just want your model to generally do well. You want the predictions to be mostly accurate. So yeah, using multiple metrics is a good thing. We want to optimize our hyperparameters. That's really what we're talking about today. And we're trying to avoid overfitting for generalizability and underfitting to promote accuracy. And then one more basic thing we talked about was splitting labeled data into the training set to build a model and the test set to evaluate the model to reduce the risk of overfitting. And that's just one split like we did last time. Today we'll do something more nuanced, which is called cross-validation. Okay, reviewing some of the basic steps here. First, you process the data. So you've got the vectorizer here to turn our words into numbers and create a sparse data frame. So that's the one that doesn't have a bunch of zeros in there. You might remember from our coverage of text as data. And then we split into train and test set. So there's a simple command you can use to do this. If you think your data is strongly nested, like you have a lot of observations that are in states and some states are more strongly represented than others, for instance, you wouldn't want to do this because this just randomizes. You're going to end up weighting the more frequent classes much more often, which could result in an inferior classifier. So in that case, you would want to do it manually like we talked about last time. Estimate the model. So in this case, keeping it pretty simple. Liblinear, this one's good for training with small data sets. This is the inverse of regularization strength, as we talked about. So the lower this is, the more strongly it's regularized, meaning there's a penalization for more complex models. It pushes things towards zero and makes the model more simple, which is usually a good thing. Otherwise, well, prevents overfitting is the point. Fit the model and data. apply it to get some predictions, and you've got the binary predictions as well as the probabilities it can output, and then get accuracy scores to evaluate performance. You could use F1 score as another thing you could do. And then interpret to identify important features. You can do this with almost any model. It looks different with different ones. So here you can just get the coefficients from a ridge model. This is L2 regularization, not what we did last time actually, but I think it was in one of the later challenges. And then the feature names are each of the column names, each of the words. Okay, I hope that's clear. I would ask for questions. If you have any at any point through this video, please post it to Piazza. I'm hoping you take a break when you need to and get some coffee. But the nice thing about having asynchronous teaching is you can pace yourself and take care of yourself as you need to. Okay, next, let's get into overfitting and solutions. So this is a key problem with machine learning. And let me get this out of the way in case you can't see the titles. Shrink this, okay, and shrink this. That should be better. Okay, so the kind of model we talked about last time relies on a statistical formula like this. There's an intercept parameter in the model, and then there's a beta coefficient for each of the words that are present in the model. So if it's got the word great, this coefficient is present. If it's got the word terrible, it's present. You could also use these with word frequencies to do the same thing. You add up all the words in this way. So just like including all of the language that's present in whatever your text data is. And then there's the error term, because no model is perfect. We want to model how inaccurate it is so we can quantify that and compare model performance. So if we try to take this model and scale it to a huge corpus of text data, how many terms would we include? How would the number compare to the number of observations? Just think about this. So if you look at even like a tweet, one tweet can have how many words? 20, maybe 30. If you think about like a longer piece of text, like a review article or a newspaper article, the words could be a lot more. Academic journal articles could be in the thousands, right? So the problem here is that in that case, even with a really small number of texts, this like approach, this equation gets enormous. Like you've got one parameter for each word, it gets huge. So, and then what that means is the model is really specifically tied to the exact data that you have. You've got a lot of terms in there, and that might be much more than the number of observations you have. And when that happens, then your model really is going to be overfit. And overfitting means something like this. You've got two classes here. You've got red dots and blue dots. This could be spam, not spam, for instance. And a model that's overfit, that's trained on all the nuances of your specific data set, is going to like try to find each and every crevice that separates these two classes. I'm hoping you can see my mouse. I haven't tested that. Yeah, so that's really great for this specific data source. But you can imagine like, what if you have a new data set? Like you've got a test set even, or you want to reuse your model in the future. Well, in that case, something more like this straight line, this more like regularized line, even that word hopefully makes sense in the visual context. Like this is exact, this is more regular, right? To reduce overfitting, we want to get something like this. And to do that, well, let me actually motivate this a little more. So the model gets overly complex, picking up on language idiosyncratic. It develops high variance is the thing, very sensitive to changes in the input. So if you trained it on a linear model on reviews of fantasy movies, it might think the word hilarious is a bad thing. It's like, oh, this plot line is hilarious. Like that scene was hilarious. That's usually a bad thing if you're talking about fantasy movies, which are usually kind of serious. Whereas the phrase Hobbit feet would indicate a positive review. But if you're looking at like all movies, the word Hobbit feet probably is an insult, and the word hilarious is probably a good thing. So you get the sense that like words have different associations, and their patterns and relationships with the classes you're trying to identify can vary. So you want to pick up general patterns without being overly focused on specific idiosyncratic language. And the way to do that is with a couple different tricks here. One is more flexible classifiers, so different ways to do this. Yeah, beyond just a straightforward linear mapping. You could do regularization, like we talked about last time, which prevents overfitting by decreasing their variance, sensitivity to noise. There's always this bias variance trade-off. Like bias is how far off the model is from the observed data, and then variance is how sensitive it is to the inputs. And regularization really just shrinks the model. So all of those many terms in that linear model I showed you just a minute ago, to go back here, yeah, each additional term here, each coefficient would be penalized. It would make the model appear perform worse, basically. And then so it would privilege models that have fewer coefficients and push things towards zero. So it would eliminate those coefficients here that don't make a difference. All the many words you can imagine, such as stop words, that don't make a big difference in terms of predicting sentiment. Okay, another way we could do this is with tree-based methods to learn nonlinear relationships. And we'll talk about that next. But yeah, first just to say, so another thing is sample splitting. So I said we talked about this. The point is to train the model on one set of data and then evaluate it on a different set of data. And you can imagine if you've got a very like fine-tuned overfit model for one set of data, your training data, and then you try to test it on something that it hasn't seen yet, it should do very poorly. That's the reason that we do this. So you can actually evaluate the model on something other than what it has already seen. And that's to make sure it's not overfed. We can do the split once, like we've done last class, or we can do it a bunch of times and then average the result. And we'll talk about that. That's called k-fold cross-validation. Okay, so next up, decision trees. So decision trees use if-then-else rules. And actually, maybe, yeah, I will show you something else in just a minute. But imagine, so you were trying to predict who survives the Titanic. There could be a couple different things we think about here, like their gender, their age, whether they have siblings on the boat, right? What the decision tree would try to do is break down each of these things based on their impact on the outcome. So let's say the most important single deciding factor on someone's survival is whether they're male or female. If they're female, then they probably, let's see, I think this is the weight. Oh, so 36% survived. The other important thing, like if they're male, the next important thing is their age. So if they're young, they probably died 61% of the time. If they're, oh, pardon me, that's, yeah, if they're old, they probably died. Interesting. Whereas if they're young and they have a sibling on the boat, which would be siblings is more than 3, they died a smaller percent of the time. Fewer than 3 siblings, they probably survived. So this is a little strange. You can imagine that male children might get rescued, put on a boat. Female children, maybe it's a different thing. But I imagine this is actually more important for the adults. The point is, there's a fork here with each factor. And what decision tree tries to do is find out which fork matters the most for the outcome and what the relationships are. So I think the next thing I have here is this. Before I get to this, let me actually show you something else that's kind of skipping ahead a bit. I'm going to show you this right here. So actually, you're going to see this in the code. This is a decision tree that we're going to train. And it looks like this. We'll talk about this data in a second after we get through the lecture. There's the activity, right? But the point here is that this language is what determines the sentiment of the text data we're going to see. It's reviews of airlines. So if the word thank happens less than half the, well, if it's fewer than 0.5 of them, yeah, and this Jenny is the score of the importance of the feature, number of times it occurs in the data. I think this is how many, like the index of the specific cases where it happens. This predicts, like, if thank is not in there, it's more likely it's going to be a positive class, positive sentiment. So I think that probably means that we're not, like, thank is usually used in the context of nobody thanked me or they didn't say thanks or something. It's usually negation. That's my guess. But let's say that's true. So thank isn't in there. Next thing that matters the most is thanks isn't in there with a similar level of importance and frequency. Okay, so that's interesting. Let's say let's say that thanks wasn't in there. Next thing is co wasn't in there. Not sure, maybe like it's referring to a group or something. No isn't in there, not isn't in there. So now we're definitely picking up on negation, on like talking about things that were wrong. Let's go the other way. So let's say think isn't less than 0.5. So think then is in the text. Next thing that matters is the word can is not in the text. That's also predicts that it's bad. If that's true, then it's also got the word but is also missing. That means it's bad. The word no is missing, means it's bad, and so on. So this is what it's trying to do. This is how the model is learning. It's like checking each of these features, looking at all the different strands, and using thresholds to try to determine which features matter. So how that looks like visually is something like this. So you've got these data points here, and you got your prediction. So there's kind of a straight line pattern with a lot of deviations. This should look very familiar to you. So it's these models are really strong in some ways because they can learn nonlinear relationships. It's not trying to estimate a sine curve. There's other models that would be able to do that more efficiently, more sort of classical models. Logit would do that really well, for instance. Instead of trying to learn like which turn to take at each point. So with each turn of the data, it's like, oh, it goes really far down here, really far down here. So a default decision tree learns these specific turns really effectively, which means results in a model that is very overfit, very finely tuned to outliers and specific turns in your data that don't represent general patterns. The general pattern here is the sine wave, which is better captured when we use a smaller max depth. In other words, like a more coarse tree is what the blue line represents. It doesn't like, the thing I just showed you had a number of layers, but if we use a max depth of 2, then it's going like this most important feature, next most important feature. So it's 1 layer and then another layer, and then it stops here. This one goes all the way down to, what are these for max depth? 4. So that's deeper than it seems like it should be. Okay, so the point is shallower trees are less sensitive to noise, have less variance. Logic here is that we take an input space comprised of some features. In the case of Titanic, could be gender, age, number of family on the ship, and then break that up into different regions with different local models. So we're trying to predict survival or mortality in Titanic case. And then learn simple decision rules in the data features. So got all these nodes, which identify the features, and leaves, which I just assign the label. So again, going back here, because I find this such a useful example, each of these is a node. It checks a certain condition, and then there's a label associated with it. This predicts a positive label, and this predicts a negative label. So whereas in the Titanic, this one predicts survival if the gender is female, and if it's male, well, let's go down a bunch of other checks here. Okay, so yeah, so we check the features and select a branch, starting with the root node until we arrive at a leaf node, a terminal node, which is where the evaluation ends, and we assign a label finally. A comparison here is random forests, which work very similarly. They're also a tree-based model. And they will just basically do this a bunch of different times. So we randomly sample from rows and from columns over all the different, take a bunch of different words in a bunch of different cases, build a bunch of different trees, and then take the average over all those predictions. This is usually slower because you're evaluating a lot more models, but the point is it's less overfit. So it provides an advantage similar to the blue line here. Instead of making the model shallow, we just train a bunch of them on different sort of like batches of the data. And it becomes less fragile. Okay, so random forest is a kind of bagging model. So we have different parts of the feature space here. We separate into different models, and then we just like average them all up in parallel. In contrast, some models are based on boosting. A decision tree model just by itself would be like a single one for contrast. So in boosting, we have a sequential process. So we take some of the feature space and we train one model, and then we look at a different part of the feature space. And with that same model, we're going to fine tune it, like try to make it more accurate. So it's not all about the first feature space or the second. It's sort of trying to do the best with both. And then starting with that model is pretty bad. We can examine the predictions for residuals. So like on the second one, how bad does it do? Improve it a little bit. Look at the next one. Split up the data a million different ways. And try to improve based on reducing errors, reducing residuals or misclassifications. Okay, so that was just a really quick rundown of the math behind decision trees, or at least the intuition. Now let's talk about optimization. So this is another sort of core thing with machine learning. So in our activity, we built something like this, where you had a function, take in, we'll train the model, fit it, get your predictions, and then put them all together. So we've got all these different models with different parameters, and we're looking at how they're doing. We scored their precision, and then we looked at their, I just stuck them all together and got something like this. So all these different cost parameters, remember this is C, which is inverse of regularization strength. And it looks generally like models that are extremely regularized, this one, don't. They're very bad. This probably just obliterates all the coefficients, and it's just like a straight line. I'm still surprised that's 0, but okay. Yeah, so whereas a 4 means not regularized at all, and it does pretty good. It looks like the local maxima here is actually this one. So pretty strongly regularized, 8, 6, 7. Yeah, so again, train the model with a bunch of different parameters, compare their precision, and get the maximum. And that's what optimization does. And so thankfully, we don't have to do like all of this code every time and just do it all by hand. There's actually something called grid search, which is an approach to optimization. It literally is just an exhaustive search over a set of possible inputs to find the maximum. So imagine like you've got a grid of all the different parameters for the cost parameter, all the different options for C, and then you've got like a grid with your different predictions and the model performance especially. So basically, you can think of the grid as being something like this. Searching over that grid to get the best one, first we have to compute all the models, but this does it basically for us. So let's say we want to search between the minimum number of samples per split. That's one thing about decision trees, is that each split needs to have at least 2 samples, or maybe it's 10. It depends on what you tell it. In each part, and each leaf, which is where sort of the tree ends. So again, looking at this is the root node. This would be a leaf because it goes and goes and goes, and it ends there. And any other leaves that show up, it looks like all of these actually continue. Oh, there's another one, and there's another one. Oh, it looks like these are all leaves. Okay, so that's the point. So minimum number of samples per leaf. So to end our sort of decision tree. Great. So these are our parameters for those. Grid search CV. So that has cross-validation built in. We'll talk about that in just a minute, how this works. But yeah, you feed a classifier, your different options for parameters, how many folds to use. Again, we'll get there in a second. And then whether you want to return a score on the training set. Fit the model and just get the best one. So much simpler code than this. I left some out here because it wouldn't fit on the page very well. Okay, so that uses cross-validation. What is that? So instead of just using all the training data at once, we split it up. Like actually in applications, if you're just doing a single train test split, usually you have your training set, your test set, which is how you evaluate your model performance. So you can like screw around on your training set, build as many models as you want, try as many different permutations as you want. Pick your favorite one based on what does well on the test set, but then you've got like an additional 10% of the data or something like that, which is your holdout set, which comes from the original data set, the whole thing, but the model has not seen this until you decide ultimately what the final set of parameters is. So that's kind of inefficient because we're splitting into 3 different pieces of data. Instead, what k-fold cross-validation lets us do is take one set of training data and one test set, right? That's it. That's the whole shebang. And we train the model on the training set. by splitting it up into different little segments. So what this does is like, you take K folds of the data. What that means is, say it's like 10. So you take 90% of a training data and leave out 10%. You train the model on 90, evaluate it, see how accurate it is using the hand labels on the 10. And then you do it again. You've got your 90 sort of somewhere else. You leave out a different 10% of the training set, do the same thing, train a model, evaluate it. You do that over and over again, and evaluate it. Say, in that case, if it's got 10 folds, you'd train 10 different models and then sort of average their performance, try to see which one does the best. And yeah, it's a way of like selecting hyperparameters. So see which one is the most accurate. That's one way you can do it. That's more of a grid search case. Actually, that's how some like models built into scikit-learn work, for instance. But in this case, all we're talking about is a single model. So let's visualize this. So you've got all the data here, split it in a training set and test set. Say this is K equals 5, so 5 folds. You split it once this way. So you've got like your training set here, and then this is the training data. So train, test it, train, test it, train, test it, and then 5 times. You can do this to find parameters, so sort of in a grid search way, or you can do it with a single model, and the point would be to evaluate the performance. Yeah, so trying a bunch, you could do this with a lot of different types of models. The point is to develop a model that's not overfit. And then again, you only do this you do this as many times as you want, but you only take the final model you derived from all this testing and evaluate it on the test data once. This is basically a held out set. So you're leaving it out completely. The advantages of this is less overfitting, and it maximizes our data. So there's in words and there it is in pictures. Okay, just some review here of our terms, in case this is all very fast and hard for you. So overfitting is when the model is trained on too little data to generalize. In that case, it would just repeat the samples it's already seen, their labels, and could seem like it's perfect on the training data, but it's actually quite bad. On anything else, underfitting is the opposite. We're not using enough of the data, or we're producing a model that's far too coarse to capture any pattern. So kind of like that highly regularized model that we saw for Logit just a minute ago, where the score was 0 because it was so strongly constrained. That's underfitting. Cross validation, we just talked about. A parameter is something that a model takes in. If often these parameters are learned through the machine learning itself. So like maximum likelihood estimation is a way of finding the peak of some kind of a hypersphere in the feature space to see what's the most likely situation that would produce the observations that we're seeing. So that's something that learns for you. It discovers the parameters as it's going. Sometimes they don't work that way. We need to tell Logit how strongly we want it to be regularized. That's a hyperparameter. That loss cost parameter is something that we choose. Optimization, selecting the best one that maximizes some output, and grid search and an exhaustive search over different model parameters that we decide. Okay, so hopefully that's hopefully that's clear, and now you have a sense of how all this stuff works. Next up is our activity. So notebook, you can click this link if you have the slides downloaded. You can go to the course repository. I'll put the link in the video if I can figure out how to do that. So next thing though is let's go over here. So here's our notebook. This time I made an outline. There's a little bit of sort of interactive stuff as well. First thing, as always, let's import some modules, load our packages. We use GraphViz here, so just highlighting that you do need to install this on your computer. So it's different from installing the Python wrapper. A wrapper is just a way of accessing something. You actually need to install the binaries, like the program itself. If you're using Linux, that would be apt install GraphViz. In fact, from your terminal, no matter what kind of machine you're using, you should be able to do that. Okay, the rest of this is machine learning, and then stuff we've seen before. Okay, so our data here is already cleaned for us. It's reviews of airlines. So let's load it in. You've got the sentiment, tweets, and then like people commenting. That's the text. Okay, so what kinds of airlines are we talking about here? We can just do a simple value counts with this is for seaborne. I just thought I'd use a different sort of figure method here. Looks like mostly they're about United, but also a lot about US Airways. Very few about Virgin America, but they're there too. Okay, so let's get to know the data a little bit, like how many tweets are in there. Let's get the length. Let's get like the distribution of sentiment. So much more negative than otherwise. Okay, how about let's normalize this. So what proportion is this out of the total? It's like 62.7% are negative reviews. Let's plot that. So, okay, that's what that looks like in terms of normalized numbers. And then what about the reasons? Like, what was the reason for so many negative reviews here? Customer service. Anybody surprised by that? I'm not. The flight was late. I can't tell, like, or it's not visible from the tweet. So these are hand coded. So, you know, sometimes it's not always apparent what the reason is. It was a bad flight or damaged luggage. Okay, so let's preprocess the data. This should be review for us, but we're talking about tweets here, so it's a little different. We got a Twitter handle pattern. We got these general patterns here. We're trying to remove things that will clog up our data with extraneous information. So remove hashtags, remove URLs, remove Twitter handles. And it does all these different things with the simple re.sub. This should look familiar to you from regex. So anything after an @ symbol, basically, any word thing, anything that's not a space. Hashtag, this is optional. There might be a space before. And then there's actually a hashtag plus some kinds of others. There's one of these, and then whatever words are immediately after this. Might be a space, that's optional. And then URLs is just anything following an HTTPS and preceding a .com. Let's see, .star.com. Yeah, this should probably be escaped like this, but it probably works either way. All right, so let's do this. Yeah, there you go. Okay, that's fine. And then let's clean it. And what do we see has happened? Clean text. There you go. So we're at Virgin America, D Hepburn. We replaced that. All right, so now let's vectorize our text. We got to turn in numbers. Classifiers learn from numbers. Made this code relatively simple compared to what we're used to. So we just initialize a count vectorizer, fit and transform it on the text, and then turn our features into an array. And it ends up looking like this. So just like a lot of zeros because it's a sparse matrix. Hooray! So this is our feature data. This is kind of what we're using to predict. This maps onto specific words, but yeah, to access that, you have to use get feature names to do that. And then our values are the sentiments. So let's just do a little check here. The length of features should be the same as the length of what we're trying to predict. Yeah, okay. So this number of lists in here, I think it is, in the array, entries in the array, which contain numbers of words, counts of words. So here we're still has a lot of zeros. It's large format. Yeah, I'm surprised to see that actually. Okay, the point is though that they have they're the same length, and that matters. So I can get rid of that for now. And then now that we've got our vectorized data, we can look at some labels and some features. That's the full set of labels. And then this is like just the first, well, not the first, it's like 500 to 510. Anyway, those are some of the words. Okay, now we split the data. Like we did last time, let's just do a single train test split here. And look at the length of each one. So the training set and the test set have the same number of columns. So that we're only including 5,000 words. I think that was because, oh yeah, I told it only include the first 5,000 words. And then they have different numbers of rows. So this is 80% of the data in the training set, 20 in the test set. Okay, so now we've split it. Let's take a look at how the outcomes are distributed. The columns are in different order for some reason. I did figure out how to fix that at some point, but I forgot. But anyway, there's like much more in the negative column. These columns are pretty evenly distributed. Even the neutral is slightly above positive. So good. This is a good check, because if the classes are not evenly distributed between your training set and your test set, then you probably have a class imbalance, and then you need to do something different, probably like a stratified sample based on your outcomes. In that case, we don't have to do that. So we're good as we are. Finally, we trained our model. This is a decision tree classifier. We're using max depth of 10, minimum of 5 samples. Oh yeah, interesting. Okay, so you're about to see what this looks like, but it should train pretty quickly. Max features. Oh yeah, early stopping. A lot of different parameters in here. It's a random seed, so that if I train this model again, it should get the same results. I'm thinking that like this max depth of 10 is the reason why the tree goes 10 deep, even though I told Expert Viz to only show 4. Oh no, that's exactly what it did. See, you never know. So it goes from the root 1, 2, 3, 4. So it did what it's exactly what it's supposed to do. That's 4 deep, but the model itself goes 10. So that's why there's more after this. Huh. All right. So yeah, we kind of talked through this already, but as far as like evaluating reviews, oh, the model turned out different this time. Well, that's randomness for you. It looks like think in this case didn't predict negative, it predicted neutral, so thanks. Whereas if hi was gone, then that's a negative review. So like they didn't say hi to me. Oh, they're so rude over customer service. Forgetting the word and seems strange to me. I'm not sure what to make of that. They forgot the word but. This is a little weird. But let's see. Oh, and if my is gone, it's neutral. So some of these things make sense to me. If worries is gone, it's neutral instead of positive. If I recall, I think the class that neutral is more common. So we don't have a lot of positive things to work with. We're mostly contrasting negative and neutral, I think. Anyway, that's enough of that. So now we've got our model here. We've got our predictions we can easily make, get our accuracy score. Great. So this single decision tree was accurate 0.704% of the time. At first, that seems to be true. The problem here is that we trained it on the training set, right? And then I just evaluate on the training set, which is bad. It's the worst thing. Then you've got a model. You actually don't know how well it does. It's like, of course, it does pretty well on this. It's overfit. If I use the test data, the part of the data that I set aside, the 20% we haven't worked with at all yet, it does a little bit worse. That's usually how it goes. Not as much worse as I usually see, actually, but there's still a difference. Okay, so more realistic, more generalizable, still good. Here's a challenge. I'm going to leave this for you to work on in class. There's a couple new reviews. You have to vectorize them using the vectorizer you trained so far, and then predict the probabilities, predict the labels and the probabilities. Okay, hopefully that's fun for you. Let's get into some basic code on cross-validation. Yeah, so we've seen, we talked about this already in the lecture. It's a way of maximizing the data that we have and avoiding overfitting. So let's check this out. So we've got a classifier, got the training data here, and I'm cross-validating it. So I want to see how well the model does on all the different pieces of training data. And then show me the average score. This takes just a little bit of time. Okay, so on our 3 different folds of the data, it looks like that one classifier had an accuracy around 0.69. We average those 3, and we see that the model was on average 0.6918. So that's better than just like evaluating it on the whole set of training data and training on the whole set of training data and then evaluating the training data. So that like is definitely going to be overfit. But in this case, we trained the model on training data and then split it up and then average performance over all the different folds of that. And we get something that's actually closer to the test set performance. So it's a little bit worse even. I guess it got pulled down. But the point is, yeah, why is it different from a classifier? Because we trained it on the different folds and then averaged it. It makes the estimates more accurate, better reflect what it's likely to see with new data out in the world. Okay, let's see more about model evaluation here. Something we can try to do is just make a confusion matrix. And that's nice. It's a little bit hard to read. Somewhere in here, you've got the ground truth and their predictions, and you get positive, neutral, negative. Let's like try a little prettification to make this work better. So this is just a heat map from Seaborn using our confusion matrix. I guess what's the main thing here is CMAP. You know what? If I didn't include this and just did the default, I wonder what it would look like. Hideous. Let's not do that. Format annotate equals true. Annotate should give me all the labels. If it didn't include that, oh yeah, ooh, it would miss the numbers in here, which are huge. I mean, it's colored by the the weight. So in most cases, the model predicts negative, and the truth is that that review was actually negative. So that's why it's dark blue, and that says the model is doing pretty good. Where the prediction was positive, it was actually positive. But still a lot of cases where it predicted negative and it was actually positive. This is a false negative. This is also a false negative because it was neutral. So just good way to look at performance. Like, again, if we're considering whether we care more about false negatives or false positives or some balance of the two, this is a great way to think about that. You can also print this kind of classification report to look at precision recall. So whereas like this is a way of visualizing false negatives and false positives, these metrics do that for you. So F1 score, which is a harmonic average, as we talked about last time, of these two. Precision, like how accurate are our estimates, recall, how many positive cases in the real set did we miss. Looks like we're capturing most of the negative ones. That's good, but we're also overclassifying negative, which often happens with imbalanced data. There's much more negative cases in the data. So it's like just going to use a baseline. We're like, oh, everything's negative. So it's going to capture most of them, but it's going to say that too many of them are negative. Some of the time in which they're not. Okay, so here you've got these averages and F1 scores. So did much better in classifying negatives than it did on neutrals or positives. The neutral is interesting to me. It looks like there are a lot of neutrals in the data that we were supposed to capture that we didn't. Yeah, it's actually precision did better in that case. Okay, so moving on to optimizations, let's do a grid search here. So as we talked about, here's our set of parameters for the minimum samples per split and per leaf. Let's do a grid search CV and fit it. And this is going to take a little while. So I'm going to keep on talking through the code here. Maximum train score. Next best. Oh yeah. So kind of like I showed you, I just take the model we just fit. So it was from the grid search and then put it into these. This I just did this way so that you could trade this out when you're running your own code for the challenges later. We get the one that has the highest score on all using cross-validation and find the best parameter values for it. So I can run this when there's time. It should show us like, oh, which set of parameters. So we've got like, it'll be 2 with 2, 2 with 10, 10 with 2, and 10 with 10. So there's 4 different sort of permutations of hyperparameters here. And pick the best one and show us what the values are, like how it scores. Okay, so once we have that, we're going to do a little visualization to see what the sort of set of possible results for the in the feature space looks like. And yeah, this is using an array. You could do the same thing here just with a list. Like you've got a list of all the different values for a number of min samples leaf vals. So that would be like, yeah, 2 and 10, and then 2 and 10. And then you get the, this just like np-empty just creates an empty array, basically, or like has some random values in there just to fill it in, but you can fill it. So then we fill this in with the set of parameters for this one, or set of results for this one, and this one as well, and then their scores. Okay, and then I provide you this function. I hope this is useful. Again, this is like what I strongly encourage as far as etiquette for writing code. Like I almost always write the documentation first because I have to think through what I'm doing. And then I can drop the things in there from the thing that I tested outside. So you test your code, you develop, what the arguments need to be. You generalize it, you write the skeleton of the function, and then you put things in there and test that. Okay, so that's what the function looks like. Oh, it ran. So good. So this is what it did. Like, yay, I ran your thing for you. Okay. The best parameter values are, 2 samples per leaf and 2 minimum samples per split, which got 0.725 on accuracy and on the training set, right? The best across the folds. And then how it was on the test set. Okay, so and then we split this up. So just to help you kind of visualize what this looks like. And then this one. Oops. So like for each of the 4 permutations, right? Let's actually put these next to each other so I can explain a little more. So again, like I said, with the combinations, you've got 2 and 2, 2 and 10, 10 and 2, 10 and 10. So we're looking at each of the different, like, we've got these 2 different arrays, which could be lists, that have 1 entry for each of the different permutations. So the reason each of these is doubled is because there's also 2 of the other thing, and we're using both. We're sort of doing a cross section or even a cross tab. I think of it that way. Okay, let's visualize this. Whoops. I forgot to run this cell. Okay, so that's what this looks like. Model performance here. So we're using accuracy. Just notice the scaling here. There's not a huge difference between these, but we're trying to maximize accuracy. So you've got minimum samples of leaf per it's 2, and then minimum samples per split, it's 2. So you go across here, go up, and then, oh, there you go. It does well. It's the best. This one goes a little bit down. So like, let's see, if we're doing leaf, I think we're doing leaf and then split, right? So it would be 2 by 10 is the second best one. Is that shown up here somewhere? No, I guess not. But they're just right there. Okay, so that's a bit of an optimization, decision trees. Now let's kind of like try one more model here, which is a random forest. As I introduced, it is well, I'm actually run the code because it's going to take a little bit to run. It's a bunch of decision trees and on different splits of the data. That's how you can think about it. And then it averages them out to produce something that's left over fit. And it looks like in this case, the accuracy 0.6189, just using the random class weight and everything that I have in here. 6189, how does that compare again? Let's see here. Our cross-validated decision tree got 6.69, and I believe the one above was similar. Yeah, okay. So this is the random forest, lovely as it is, and less likely to overfit, did much worse. So good to know. I would hesitate to say that's a worse model. In fact, it's probably more generalizable. Yeah, and once like you usually train a model and then you apply it to data that you haven't seen. Like you do something with it. So I would probably still trust this one more, but let's like try this out. So a couple of challenges for you when you get to class is to do a grid search using this model and different levels of the same things that we tried. I encourage you to kind of, experiment, try different ones. And find what the best permutations are. I'll say that class weight matters here. If you try it with a different class weight, like if you look at the solutions, I used balanced subsample actually, it will change the performance. Also, randomness matters. So even though I use a random state. So yeah, experiment, have fun. The other challenge here is about text preprocessing. We just counted things, but you could try without removing usernames, hashtags, URLs. Maybe that's actually an important signal. And we should consider leaving that in there because it helps differentiate, the sentiment. So yeah, preprocessing is not one size fits all. There's different ways of doing this. And the last thing here, if like you feel like you want a challenge, you don't need to submit this when you post to Canvas, but AdaBoost is a boosting model. So instead of like training a bunch of different folds with their own models, you train one and then iterate over and refine it with each fold. So you can try that here and do a 3D visualization and a grid search if you want. Okay, so let me stop sharing. Great to see you all. Sorry to miss you today. I hope you enjoy your time with Ramsey. And yeah, see you online and next week. Good luck with your projects and your last problem set. See you later.